Hello, in this video I will be discussing the conformations of cyclohexane in particular. You may remember that we talked about the fact that cyclobutane, cyclopentane, and so on can pucker up a little bit. Cyclopropane is not able to. Cyclobutane can pucker a little bit into what they call butterfly conformation, but at the cost of a little bit more angle strain. Cyclopentane can pucker up some into what they call the envelope conformation, but at the cost of a little bit more angle strain and so on. But cyclohexane is very stable in that when it does pucker, it not only relieves some or all of the torsional strain, in other words, the hydrogens all become staggered instead of eclipsed, but it also relieves some or all of the angle strain, so that the angles are all 109.5 or very close to it. So it turns out that cyclohexane exists as two very stable chair conformations, and I have a model of a chair conformation here. You saw this in a previous video. Notice that if I hold it this way, these three carbons are slightly higher and these three carbons are slightly lower, and the angles, the bonds in the ring kind of go up, down, up, down, up, down around the ring, and these three hydrogens are pointing straight up and these three hydrogens are pointing straight down, and then you have 6 around the outside. Every carbon has 2 hydrogens on it, one that's pointing straight up or straight down, and one that's pointing out to the side. This is what's called a chair conformation. Now, when I say two very stable chair conformations, it turns out that this can actually rotate around single bonds into a different chair conformation. It'll look exactly the same as long as these are all hydrogens, but it's not easy to do because it requires a lot of energy. Flip it to the other chair conformation, which, as far as you can tell, looks the same as the first chair conformation, but what was axial has become equatorial and so on. So there are two, and there are also what we call boat conformation. Example of a boat conformation here, where these 4 hydrogens are all pointing down, 2 of them on opposite sides of the 6-membered ring, so you have a 6-membered ring. These 2 are kind of butting heads against each other, even though they're on completely opposite sides of the ring. The whole thing kind of twists up onto itself, and this is what's called a boat. And I don't know if you can see the little boat in there or not, but we'll look at some structures here in a minute that look a little bit more like a traditional boat might look. But then there are also what we call twist boat conformations, in which the boat is just twisted off a little bit, so these 2 twist away from each other slightly. So now we have what's called a twist boat conformation. Looks almost the same, except you'll notice that these 2 bonds that were parallel are now just twisted a little bit, not parallel. So that's a boat conformation and twist boat conformation. Now the interconversions, and all those will convert into each other, so you can turn each of the 2 chairs into each other, and all the various boats into other boats, and twist boats into other twist boats, and so on. They can all turn into each other simply by rotating around single bonds. So those are what we call conformations or conformational isomers, kind of similar to the transitions we saw between staggered and eclipse conformations, except when you're doing a ring and you want to flip from one conformation to another, you have to actually rotate all the bonds in the ring at the same time. We'll see how that happens here. Now, here are diagrams or things that you can draw on your paper to show the various things that I've shown. These are the 2 chair forms. I've called them chair 1 and chair 2. They look like they're exactly the same, except sort of mirror images, or maybe just turned around 180 degrees. But this is to suggest that this carbon in one of the chairs is this carbon in the other chair. And we'll see how when you flip one into the other one, this group that's pointing up on this carbon will become this group on the other ring, and so on. Now this is how you draw a boat, and this is how you draw a twist boat. Notice there's kind of an X shape in the middle. And then there's this thing called a half boat that I didn't mention before. That's really how one chair turns into the other chair, is by going through a half boat. And a half boat is really very unstable. It has a lot of energy in it because now the angles are all wrong, and there's a lot of eclipsed hydrogens and other groups in here as well. So in an energy diagram, the chairs are always the most stable. Now in this particular diagram, they're the same energy, but in some cases, if there are groups on the ring other than just hydrogens, then the chairs may not be the same energy as each other. And later on, we'll learn how you distinguish which of 2 possible chair forms is higher in energy or more unstable. Then this is a half boat, so that to go from one chair to the other, there's a big energy barrier in there. And you saw me struggling a minute ago to turn one chair into another chair. It's because the energy barrier is so high between them. Also, if you go over that same energy barrier, you may end up with a boat. So you can go from a chair to a boat form. Actually, twist boat is the bottom of an energy well. It's a little bit lower in energy than the boat itself. In fact, the boat is really a transition state between one twist boat and another twist boat. Now, you're going to have to be able to draw cyclohexane chairs, and to some extent boats, but mostly chairs since they're the more stable of the formats. You're going to have to be able to draw them on your paper, as well as show how would you flip one into the other. So what we're going to do here is have a little tutorial on how you draw cyclohexane chairs. So first what you do is you draw two lines tilted a little bit and one right on top of the other. So this end of the dash is right above that end of the dash and so on. Then you put in a dot, one dot here and one dot here, just a little bit above the end of that line, and this one just a little bit below the end of that line, but off to the sides a little bit. And if you're doing the other chair form, the mirror image one, just put the dots in the opposite positions. Then connect the dot to this end and the dot to this end, this dot to that end and to that end. And now you have a nice chair skeleton. Same thing on this side. Then we're going to put the groups that are attached onto these rings. So what you're going to do is put 6 vertical segments on this ring and or 6 vertical segments on that ring. They will go one on each carbon. So this gets a vertical segment up, this gets a vertical segment down, this gets a vertical segment up, this gets a vertical segment down, and so on. In other words, the ones where the carbon is already pointing slightly up above the rest of the carbons gets an up vertical one, and the ones like this one, and this one that are already slightly pointing down get a down segment. Now, the ones that are tricky are this one, because you have to draw it so it's sort of inside the ring like that, and this one. If you want to, you can actually extend that a little bit beyond the ring, but if you do, you have to put a little break in there so that you're showing that that's actually in front of this bond. And of course, once you've done the chair flip from this form to this form, then you have some different groups on the carbons in question. This one straight up, this one straight up, and this one straight up that I've been referring to as vertical, also called axial, and this one straight down, this one straight down, and this one straight down, also called axial. Vertical groups are always called axial. I guess I should mention the way these rings on paper are drawn, it's to imply that these two carbons are kind of in front, these two carbons are kind of behind. So for example, if I had to look at my chair form here, notice that these two carbons that are in front are these two carbons in front here, and these two carbons pointing to these two carbons back here are the ones that are back here. This one is this one, and this one is this one. Then, once you have your vertical dashes placed properly, then you're going to put a diagonal dash, also one at each of the 6 carbons. So the one at this end where you have the carbon of the ring pointing slightly up, it's got a vertical dash up, it's going to have a diagonal dash slightly down and pointing to the right. This one that has the carbon is pointing slightly down, notice that that's a sort of a down angle there, has a vertical down, it's going to have its diagonal up and pointing to the right. Don't draw it over here because it's on the right hand side of the molecule, its dash is going to point to the right. And same thing here, it's got a vertical down, it's going to have a diagonal up slightly at an angle and pointing to the right. So all of this stuff is on the right, it points to the right. All of this stuff is on the left, it points to the left. So at this one where you have a vertical down, you'll have a diagonal up. And here where you have a vertical up, you'll have a diagonal down, and so on. So this is what the one ring would look like, this is what the other ring would look like. And you should practice drawing these two rings because it's really important and it's difficult, there's no question about it. But if you practice it, you can get your ring so that they're looking pretty good. And if you want to, you can always pause the video at this point and just draw structures that look like these two until you're good at it. By the way, we're going to refer to these, the ones that are straight up and down. Instead of calling them vertical, we're going to refer to them as axial, because they're going to be, if you think of this ring as a globe, here's the axis of the globe, North Pole, South Pole. These 6, 3 up and 3 down, that are vertical are parallel to the axis. So in my model here, these 3 pointing up and these 3 pointing down, that I have my fingers on, are the ones that are straight up and straight down, or they are going to be called axial because they're parallel to the axis of the molecule. These 6 around the outside that are pointing slightly down, slightly up, slightly down, slightly up, and so on, that I've been referring to as diagonal, we're going to call them equatorial because they're around the equator of the globe. So the axial ones are parallel to the axis, the equatorial ones are around the equator. So here we go. The ones that I've labeled with a red R on the screen are the ones that are going to be axial. So there's an axial up here, an axial up here, an axial up here, 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 and here. And then the ones in green are the equatorial ones. So I have a model here that corresponds to the structure that you see on the screen. So the 6 red ones, 3 of them are up and axial at alternating carbons. So this one's up and axial, this one's down and axial, this one's up and axial, this one's down and axial, and so on. So 6 axial ones, 3 up and 3 down. And then 6 equatorial ones. This one, this one, this one, this one, this one, this one, and this one. Around the outside, notice they're slightly up, slightly down, slightly up, slightly down, and so on. Now, here's what happens when you do a chair flip. This is going to be a little bit tricky, so keep your eye on what I'm doing here. Notice, and again, memorize this picture, the red ones are axial, and the green ones are equatorial. Now, I'm going to try to do this without breaking any bonds. It's tricky because there's that big energy barrier there, but if we flip this, I'm now at a boat. Move up again. And I'm back to another chair form. And notice what happened. Like magic, the red ones that were axial became equatorial, and the green ones that were equatorial have become axial. So every time you do a chair flip, the axials all become equatorials, and the equatorials all become axials. Does that happen in real life? Absolutely. So in an actual sample of cyclohexane, it's doing this flip all the time. So the axials are becoming equatorials, and the equatorials are becoming axials constantly. Flip it back and forth many times per second. One thing you should notice, though, and this is very important, if you don't turn the molecule upside down, but you keep it in place, what was up stays up, and what was down stays down. So notice that this carbon right here corresponds to that carbon right there. The red one right here that was up and axial became this one, which is still up. It's only slightly up, but it's still up. So the up axial becomes up and equatorial. And notice that this green one at this position that was up and equatorial becomes this one, which is up and axial. So what was up stays up, what was down stays down. In other words, you can't rip them all a group off the top of a ring and stick it on the bottom. You could turn cis into trans, and we've seen before that you can't do that. Let's do a chair flip again, and keep your eye on this green ball right here. In the molecule as I have it now, it's up and axial. So I'm going to put a yellow ball on it, and notice that it is, if I hold the molecule this way, up and axial. Now I'm going to do a chair flip. I didn't turn the molecule over, I just rotated around the single bonds, the 6 single bonds in the ring. And what location does the yellow ball have now? Well, now it's equatorial. It's not sticking straight up or down, but off to the side, but it's still slightly up. So remember, it was up and axial, now it's up and equatorial. So what was up stays up, what was down stays down, axial becomes equatorial, equatorial becomes axial. It's really cool how this works. What I've done here is I've shown the red ones that were axial becoming equatorial, the green ones that were equatorial becoming axial, and this is all together. The reds that were axial and the greens that were equatorial become reds now equatorial and greens axial. So watch each particular position, and really you have to pay attention to each location on each carbon in both of the ring forms. At this carbon, we have a axial up, it becomes equatorial up. At this position, we have axial down, it becomes equatorial down. So again, axial group down becomes equatorial group down at that particular carbon. So again, that carbon becomes that carbon. At the next position, this one, axial up becomes equatorial up. The next one, at this far position over here, the one furthest to the left, axial down becomes equatorial down, and vice versa. At this carbon around the back, axial up becomes equatorial up. It's tricky. This carbon becomes that carbon. People want to make that carbon become that carbon, but it's not. The one that's furthest to the left is the one that's furthest to the left once you do the chair flip. So that carbon with its up axial group becomes that carbon with its up equatorial group. And finally, this carbon becomes this carbon. The R group, the red R group, which was axial and down, there becomes equatorial and down. Again, in all of those cases, what was axial becomes equatorial, and what was equatorial becomes axial, but down stays down and up stays up. Let's go through the other alternate ones. This was green, and it was down and equatorial. It becomes down and axial. Again, notice the carbon that's furthest to the right is the carbon that's furthest to the right. The next one, this carbon had an equatorial group up. It becomes axial and up. Next carbon over had an equatorial down, becomes axial and down. Next carbon up and equatorial becomes up and axial. Next carbon down and equatorial becomes down and axial. That's a little tricky because it's back behind there. Finally, this one that was up and equatorial becomes up and axial. Now, let's do a real case. For example, let's try drawing trans 1,3-dimethyl cyclohexane. So this is a flat, what I call a planar projection. It just looks like a hexagon. We're looking at it from the top of the molecule, looking down on it, so it looks just like a hexagon. But it has two methyl groups at carbons 1 and 3, so it's 1,3-dimethyl. One of them is on a wedge, so it's up. The other one is on a dotted line, so it's down. Now, what you need to do, perhaps, is stop the video and write on this structure, put a methyl group, and then count around to the third carbon and put another methyl group. Make sure one of them is up and one of them is down. And then do the chair flip. So wherever you had an up axial group, it becomes an up equatorial group. Wherever you had a down equatorial group, it becomes a down axial group, and so on. So stop the video and see if you can put in two methyl groups on this structure and two methyl groups on this structure. Now here's what I'm going to do, and you may have chosen a different carbon, but I usually like to start at this carbon right over here, the one that's furthest to the right in this structure, and I will just put whatever group I want to start with on the axial position. You'll notice that it's up here. That would then be this one that's up here. And that's because, to me, that's the easiest carbon to kind of see what's going on there. So I'm going to say that carbon is that carbon right there, and since its methyl group is on a wedge, it's going to be pointing up. Then count around, since that was carbon number 1, that's 2, that's 3. Count around carbon 1, 2, 3, and put another methyl group on carbon number 3 down, because it's on a dotted line. So would that be this, or would that be this? Obvious answer, that. So we put a methyl group right there in the down equatorial position. So there we go. We have put our two methyl groups on, one up, one down, one at carbon 1, one at carbon 3. Now we need to do the chair flip on paper and put in the two methyl groups on this structure so that they correspond to the carbons that are in this structure. Here's the key. That carbon right there, which we've called carbon number 1 in that structure, is that carbon right there. We're going to call it carbon number 1 in that structure. So there we go. And we put a methyl group in on that carbon. And because it was up here, it also has to be up here. So that's on this equatorial group, not that one. That's down, obviously, so that must be the up one. And so since this was up and axial, it now becomes up and equatorial. We know that that's what happens in a chair flip. What was up stays up, what was down stays down, what was axial becomes equatorial, and so on. Then we need to count around to carbon number 3, so that's going to be this one. And because this methyl group was down and equatorial, now it's down and axial. So we have completed the job of putting in the two methyl groups. By the way, these other dashes that are shown around on the ring would be hydrogens. You can put them in or not if you want to. So at this point then, you will generally be asked to decide which of the two chair conformations is more stable. In other words, which one will predominate in equilibrium. That may not be part of the problem, but in most cases it will be. And so you have to compare your two chair forms. Now we know this molecule is actually flipping back and forth between these two chair forms. but looking at them, we have to decide which one's more stable. This conformation, I'm going to call it A, has an axial methyl group and an equatorial methyl group. In this conformation, we have an axial methyl group and an equatorial methyl group. So in fact, they are equally stable in this particular case. Now, it's not always going to be true. In some cases, you may have more axials than equatorials. That one that has more equatorials is going to be more stable. So rule number one, equatorial is always lower energy than axial. So if we just had methyl cyclohexane, this would be the two chair forms. One would have an axial up, the other one would have an equatorial up. Which one is more stable? Well, the rule says equatorial is lower energy than axial, so this one would be more stable. And this one would predominate in equilibrium. And in fact, in a sample of methyl cyclohexane, it is true that there are two chair conformations, but this one far predominates over this one. Now why? Why would an equatorial one be more stable? Because in an axial situation, this methyl group is actually interacting to some extent with this hydrogen here and this hydrogen over here. Whereas in an equatorial situation, it's just sticking out here like a sore thumb, not very close to any of the other groups. Here's another rule. Larger groups axial are higher energy than smaller groups axial. So notice in this particular case, we have a propyl group up and axial, and way over here on the fourth carbon, a methyl group also up, but equatorial. So a propyl group axial, a methyl group equatorial. If we do a chair flip, the propyl group that was up and axial becomes up and equatorial. The methyl group that was up and equatorial becomes up and axial. So looking at 1-methyl for propyl cyclohexane, there are these two chair forms, but this one predominates in equilibrium. There's much more of this than there is of this. Why? Because here the bigger group, the propyl group, is axial. Here the bigger group, the propyl group, is equatorial. And bigger groups want to be equatorial more than smaller groups want to be equatorial. So the fact that this group wants to be equatorial forces the methyl group to be axial because it's smaller. But that's better than having a propyl group be axial. Now, try this one on your own. Cis 1-ethyl 2-methyl cyclohexane. What you're going to need to do is draw the two chair forms, put in all the axial and equatorial positions, decide where will this one go in one of the chair forms, and therefore where will this one go in that same chair form, and then do the flip and see which one is more stable. And we'll stop at that point, and if you want to go over that in class, we certainly can do that. Thank you for your attention.